All right, let's dive into the wild world of superacids. We're on a mission today to uncover 5 fascinating facts about these chemical powerhouses, especially that glass-eating champ, fluoroantimonic acid. You know, if regular acids are like the vinegar in your kitchen, superacids are, well, the stuff even chemists treat with extreme caution.
That's a pretty good way to put it. They really are in a whole different league when it comes to potency. We're talking millions of times stronger than sulfuric acid, which is already pretty corrosive on its own.
Millions of times. Whoa, okay. So what gives them that kind of insane strength? What makes them so much more powerful than, like, your everyday acids?
Well, it all comes down to protons.
Protons, like the things inside atoms.
Exactly. Acids are all about donating those little positive charges, those protons. And superacids, well, they are the ultimate proton donors. They're so good at giving away those protons, they can protonate almost anything, even substances we usually think of as totally unreactive.
So they're like the overachievers of the chemistry world, always ready to share their protons.
Haha, yeah, you could say that. And when it comes to overachieving, fluoroantimonic acid definitely takes the prize. This stuff is so strong it can actually eat right through glass.
Okay, yeah, glass-eating acid, that definitely fits the super description.
Yeah.
But what makes it react so violently with glass? Like, what's going on at the molecular level?
Well, fluoroantimonic acid is a combination of two things, antimonyl pentafluoride and hydrogen fluoride. And get this, the bond between them is incredibly weak, making the whole molecule extremely reactive. It's like desperate to grab onto something. And, well, the silicon dioxide in glass happens to be a perfect target. It just tears it apart.
So it's like a super hungry molecule on a mission to bond with anything it can get its metaphorical hands on.
Pretty much.
Now, here's something I found really interesting. Unlike most acids we encounter, fluoroantimonic acid doesn't need water to do its thing. It can react directly with organic compounds, which I imagine makes it even more dangerous.
Right, that's a key difference. Most acids need water to create those reactive protons we were talking about. But fluoroantimonic acid, it's so strong it can skip that step altogether. It can directly protonate organic matter without water's help.
So it's like a one-man army, just cutting out the middleman and going straight for the target.
Exactly, and it's incredibly powerful. Get this, fluoroantimonic acid can even dissolve noble gases.
But wait, noble gases.
Yeah.
But those are famous for being completely inert. Like, nothing reacts with those guys. How can anything dissolve them?
Yeah, it's pretty mind-blowing. So noble gases usually don't react because their outer electron shell is full, making them very stable. But fluoroantimonic acid comes along with its proton-donating superpowers and disrupts that stability, forcing even these noble gases to react.
Wow, that's just incredible. So we've got this insanely powerful acid that can eat glass, react without water, and even dissolve noble gases. What could we possibly use something like that for? I mean, it sounds more like something out of a mad scientist lab than anything practical.
Well, you might be surprised to hear that fluoroantimonic acid actually has some important industrial uses, particularly as a catalyst in things like fuel processing.
Okay, so we're harnessing the power of this chemical beast for a good cause.
Yeah, exactly. Catalysts speed up chemical reactions without being consumed themselves, and fluoroantimonic acid is a highly effective catalyst for certain processes like alkylation and isomerization, which are crucial for refining and improving fuels.
So it's helping us create more efficient and sustainable fuels.
That's right. It's a really interesting example of how something so potentially dangerous can also play a vital role in, important industries.
It's definitely a reminder that chemistry is full of these kinds of fascinating contradictions.
It's funny, because for something with a reputation for being so destructive, superacids can actually be pretty selective in how they react.
So it's not just a matter of them, like, dissolving everything in sight. There's some nuance there.
Exactly. It all comes down to understanding the specific properties of the substance and how those interact with the superacid's proton donating ability.
Right, so it's not just brute force. It's more like a delicate dance between the superacid and the substance it's reacting with those protons leading the way.
Yeah, a good way to put it. And by carefully controlling the conditions of the reaction, chemists can use superacids to make some really remarkable transformations.
So superacids are more than just like powerful solvents. They're like um, versatile tools that chemists can use to really manipulate and create new molecules.
Exactly. Their ability to, to kickstart and speed up certain reactions makes them super valuable in fields like organic synthesis, where chemists are always trying to make new compounds.
It's fascinating, isn't it? It's like it seems like superacids are helping us really push the boundaries of chemistry.
Absolutely. And the potential uses, they go way beyond what we've talked about so far. Like people are looking at using them for everything from, new materials to clean energy.
So we could be seeing superacids playing an even bigger role in the future in like a whole bunch of industries.
Oh yeah, definitely. There's tons of research going on right now into using them for like, advanced polymers and catalysts for renewable energy and even new pharmaceuticals.
It's incredible to think that something so powerful, so potentially dangerous,
Mm.
could also be used for so many, beneficial applications.
Yeah, it really highlights the duality of chemistry, doesn't it? How even the most potent substances can be powerful tools for progress if we understand them and use them responsibly.
Okay, so we've talked about the strength, the reactivity, and some of the applications of superacids. Is there anything else that really makes them stand out? Like what sets them apart in the world of chemistry?
Well, one thing that's really unique is the environment they create for reactions. Superacids can actually stabilize certain types of really reactive molecules that would normally be impossible to isolate or study.
So it's like they create a protective bubble where these reactive molecules can exist and be observed.
That's a great way to put it. And by stabilizing these elusive species, superacids give chemists a chance to really understand the fundamental workings of
It's like
reactions.
opening a window into the world of molecules, isn't it?
Exactly. And this ability to stabilize those highly reactive species has led to some major discoveries, especially in areas like carbocation chemistry, which is crucial for understanding organic reactions.
Wow, it seems that we've only just scratched the surface of superacids and their potential.
Oh yeah, there's still so much more to learn and explore about these remarkable substances.
This deep dive has definitely given me a new appreciation for superacids. Their power, their versatility. But I'm curious: are there any drawbacks? Like, are there challenges associated with working with these incredibly potent acids? I mean, it sounds like working with these things must come with some serious safety concerns.
Oh yeah, absolutely. Handling superacids, it definitely requires a lot of caution and
Hmm.
specialized equipment. They are incredibly corrosive, as we've been, discussing, and can react very violently with lots of substances, including water.
So yeah, no accidental spills in the lab. What kind of safety measures do you have to take when you're working with these acids?
Well, you have to start with materials that can handle that corrosive nature. So you're talking specially designed glassware, often coated with things like Teflon,
Yeah.
and even then you have to be super careful.
It kind of sounds like handling a dangerous animal or something. Like you need the right tools and a lot of respect for their power.
That's a good analogy. And in addition to the right equipment, personal protective gear is essential. Gloves, lab coats, face shields, you name it. And a lot of times the work is done in fume hoods to prevent, accidental inhalation of any fumes.
So it's a combination of physical protection and controlled environments. Are there any other challenges beyond the safety stuff?
Well, their extreme reactivity, while it's super usable, can also be tricky to manage. It really takes a deep understanding of the chemistry to be able to control and direct that reactivity, to get the outcome you want.
It's like you're a conductor or something leading an orchestra of highly reactive molecules. You need to know exactly when and how to cue each instrument.
Haha, yeah, exactly. And just like a conductor has to consider the characteristics of each instrument, a chemist working with superacids has to carefully select and control the conditions of the reaction. So things like temperature, concentration, the presence of other substances.
So it's a real balancing act, isn't it, between harnessing that power and uh, making sure they react in the way you intend them to.
Exactly right. But even with all those challenges, the potential benefits of superacids continue to drive a lot of research and innovation. And I think, as our understanding of these acids grows, so will our ability to use them safely and effectively.
Well, this has been an incredible journey. I feel like I've learned so much about superacids their strength, the way they react, their applications, and even the challenges of working with them.
It's pretty amazing to think that, these substances that can dissolve glass and react with noble gases can also be used to, develop new materials and create cleaner fuels and even push the boundaries of chemical synthesis.
It really shows you the power of chemistry, doesn't it? The
Hmm.
potential for both creation and destruction.
Absolutely. And, that's why it's so important to understand and respect these substances.
Well said. I want to thank you for joining me on this deep dive into the world of superacids. We hope you've enjoyed it and learned something new along the way.
The pleasure was all mine.
And to all our listeners, keep exploring, keep asking questions, and keep that spark of curiosity alive.
Hmm.
Until next time.